Now for example 4, I want to find the mass of the solid bounded by x equals 0, y equals 0, z equals 0. So I'm obviously putting myself into an octant there. And then y equals e to the negative z. And x equals 2 and z equals 1. Whew, that's a lot of functions. So given the density function, delta is equal to x plus 1 with the units of grams per cubic centimeter. Okay, so I graphed this in Maple because we are going to be finding the mass. So what I did was I graphed pieces of it. So I'm graphing the 1, this is plot 3D, so this is z. So z equals 1 from 0 to 2 because it said z was equal to 1. Then I'm also doing, and I wanted to get cutesy about it, because y was equal to e to the negative z, so I solved that for z, and I got the natural log, sorry, the negative natural log of y. So I reversed that order. That way, because when you do plot 3D, it's automatically z equals. So this way it was a little bit easier for me. And then I solved it slightly differently. I solved it for the other function. EXP, by the way, stands for E, in case you're wondering. And then for plot 3D down here, I did P3 right there. And then I displayed all three of them together. So it gives you kind of a sense of what it looks like. So you got your x-axis over here, right there on the left side. You got your y-axis back there. You got your function right there with the lovely rainbow color. And there's z equals 1. So it got cut off at the top at z equals 1. And then you can see you're casting a shadow down onto the xy plane. That's just the way I think of it. So that's my shadow right there. The 0 is down onto the xy plane. And then I gave it limits that restrict it to what I know must be the case. Now, how did I find those? How did I know that? Well, you set the things equal to each other. So let's see here. So I knew that was the object. Oops, let me just delete all of this. Right? So you set the two equations equal to each other. So you say, okay, well, I'm going to let 1 equal, right, z is equal to 1, so e to the negative 1 is y. So then that means that you could take the log of both sides and so on. That's where I've got my limits of integration from for over here, that kind of stuff, right? So I'm solving for that by setting 1 equal to e to the negative z, right? Sorry, y equal to e to the negative 1 and solving it, which means y is equal to 1 over e. E of 1, remember, is exponential to the 1, so it's exponential. It's Euler's number, e. All right, so let's see here. I've got my function. I've got a lovely picture of it. It sort of matches my Maple picture. Let's look at my Maple picture. Yeah, there you go. Right? So I set my equation equal to 1, or I set z equal to 1. I solved it for y. I got my values in there. Then I told it to graph from there to there. And so it did. Right? So y goes from 0 to that value. And then z goes from 0 to, well, 0 to 1 for some of it. All right, so now how do I find that? Well, the region, luckily for me, is a rectangle again. I love rectangular regions. It means that everything is constants. So the z is going from 0 to 1, the x is going from 0 to 2, and boy, does that make life a lot easier for us, right? Okay, now, but what about the y, right? The y is changing right here. So I'm going to have to look at my function and do it with respect to y first. And by the way, just so you notice, the region that we're doing here is not, here, let me show you. It's not the gray zone down here that's on the xy plane. It's over here. It's on the back wall over here, which I couldn't figure out how to draw that. But it's that white space right there on the xz plane. You're actually building your volume up from over here on the xz plane up to that curve y. You're not going from down on the bottom of xy, and the reason you're not, nor would you want to, is because you'd have to do two sets of triple integrals. You'd have to do one set of triple integrals from 0 to wherever this red region ends. Then you'd have to do another set for the curvy part. Well, that's too much of a pain. It's much easier if we go from this back plane back here on the xz plane and build our columns up from there to find our density or our volume, our mass, right? Sorry. mass because we already have density. So we're going to go from that back plane xz up. And you can see that's kind of how I drew it on the picture. So that's that orange column. We're stacking from the bottom of the xz plane. So that's your xz plane out to where the curvy part is, which is y equals e to the negative z. Okay, now our density function is x plus 1. So for once, for the first time ever, we are going to feature a function that is not 1. It is x plus 1 because that's what delta is. So delta was x plus 1. And I'm going to go with respect to y first because y is the part that's varied. It's got the curvy part. And again, I don't want to do what I've done in the last ones. I did z first. I was stacking from the xy plane up to the curved part. I don't want to do that here. I want to go from the xz plane over to that curve. So I'm going to go with respect to y first, which is nice because we actually have functions with respect to solve for y already. Namely, we have y equals e to the negative z, and of course the xz plane would be y equals 0. So I'm going from y equals 0 to e to the negative z. There's my two limits of integration for y. And then the x and the z are super easy because it's a rectangular region back there. That pink region right there is rectangle. So I'm going from 0 to 2 for my x and 0 to 1 for my z. All right, well, why the zeros? Well, 0 to 2 for x because it's given. It tells you they want x from 0 to x equals 2, z from 0 to z equals 1. I mean, they're practically giving you in these instructions right here all the limits of integration. It's all there. It's just a question of deciphering it and realizing that unlike a lot of these, we're not going xy plane up, we're going xz plane to the right, right? For that column. You're moving, and I like to show it with that arrow. So I'm showing that's the way I'm going. On this one, I want to show up because that was the way I was moving. Okay, so integrating x plus 1 with respect to y will be really easy because there's no y in there, so it's just x plus 1 times y, right? And then you're going to put 0 and e to the negative z in there. And then you'll notice there's no, there's an x in here, there's a y in here, there's a z in here. You're not going to be able to do the trick that we've done on the other problems where you can cancel out one of your variables and one of your differentials. It's not going to happen. So you have to keep everything in play because you haven't gotten rid of one of your variables yet. So I'm going to put in e to the negative z for y and then minus 0, but 0 times it is going to cancel. So that's just gone. So that leaves me x plus 1 e to the negative z. Notice there's still an x and there's still a z. So I can't cross off and put a 1 in front or cross off and put a 2 in front the way I did for this one. But this problem had no x left, but this one does, right? So now I'm going to integrate with respect to, I think, x. I mean, it kind of doesn't really matter, but I'll go with respect to x. All right, so if I integrate with respect to x, I get 1/2 x squared plus x from times e to the negative z from x equals 0 to x equals 2. Well, again, the zeros are going to cancel out, so we don't really care about any of that. So you just put the 2 in, right? 1/2 times 2 squared plus 2 makes 2 plus 2, which is 4. So you're left with 4 e to the negative z from 0 to 1, and then integrate that, which is negative 4 e to the negative z from 0 to 1, and that's your answer. So negative 4 e to the negative 1 plus 4. And I will prove it to you with, oh, I was just fiddling around with other ways to plot this. So you can mess around with that. But there you go. The integral, this is the integral you're originally given. X plus 1 is your density function. You're going from y equals 0 to e to the negative z. So that's how you type it. If you don't want to use the palette, you type exp negative z and it means e to the negative z. Or you could use the palette exponential expression, right, for Euler's number, either one. And then you have x equals 0 to 2, z equals 0 to 1. If you would like it numerically, you can type common numeric. There you go. And then just to prove to you that the last integral, that I'd done everything else correctly, there's the last integral we did, and sure enough, it gets the same answer as what I came up with. So I integrated correctly. I would not lie to you.